In this lecture, we're going to go over the chemistry test that we are going to be determining to find out what is the health of the body of water that we're studying. And we'll apply this to the Middle Fork River most of the time. One of the things we'll look at is turbidity, or pretty much how dirty or how murky is the water. Here we can see what's called a turbidity flow or turbidity current that's moving into, let's just say, cleaner water. Clearly different in terms of what you see visually. Right? You actually can see the sediment that's suspended within the water. The importance, because turbidity is simply the result of sediment or organic debris that's suspended in moving water. And this can impede the breathing, right? Plants and animals, they need to breathe. So this can impede the breathing because it can block gills, it impedes filter feeders, and as importantly, it blocks sunlight that leads to reduction in photosynthesis. So when we look at values, there's a value, there's an ideal and optimal amount of a little bit of turbidity, but not completely clear. And the more turbidity there is, well, let's just say it decreases the value of the health. For temperature, too high, right? Warm water can eliminate cold water organisms from living in the water, and less oxygen dissolves in higher temperatures. We'll find out that dissolved oxygen is temperature dependent. And what it means by that is that the warmer the water, the lower amount of dissolved oxygen that can be held within the water itself. So where does it come from? Sometimes there are hot water discharges. Some power plants, different industrial plants, can crank out really warm water, and this can lower, well, let's just say it can heat up the water. And also areas of a river or a body of water that lack shade. So if it's just basking in the sun, it's going to be warming, and that warming trend is going to be decreasing the chemistry of dissolved oxygen. So there are these optimal temperatures here, and we will find that there are certain parameters that we want to make sure the temperature should be at to be healthy, maintain health. pH. This is an indication, right? You've probably heard in the past, acidity are low pH values, 7 is neutral, and higher than pH of 7 are going to be alkaline or basic. So we can look at this. So what are the sources? Well, acid rain, mining, and or the presence of limestone. Limestone locally actually buffers, right? It buffers pHs. So there are specific pH values. We should not have any issues with pH. We don't have anything that really is going to be adding or driving acidity values to deviate too far from a neutral pH or a pH of 7. Dissolved oxygen. This is what organisms breathe, right? Oxygen. It's just found in the water itself, just like in the atmosphere. And this is a byproduct of photosynthesis, and it also mixes in from the air when water is turbulent. So our riffles help increase or add dissolved oxygen. And we'll find that dissolved oxygen is the single most important value for calculating the health of a body of water. So some values, if it's between 0 and 3 parts per million, oops, that should be parts per million, few organisms can survive. And where we have 3 to 4, only a few can survive. 4 to 7 is kind of the low range, and I would say 5, 5 is the EPA, the Environmental Protection Agency's suggested lower limit to maintain healthy aquatic biota, and greater than 7 are very, very few species can survive with that. Nitrates, the importance, promotes growth. Excessive levels can lead to eutrophication and kill fish and reduction of biodiversity. Here you can see there's something going on in the water. This would actually be from the excess of nitrate. Right, when fertilizers run off into bodies of water, this can lead to the increase in algae, and this leads to eutrophication. We'll get into what eutrophication is very soon. So nitrate, we want to make sure that that value is within the healthy range, along with phosphate. And nitrate and phosphate often go together, but they can have different sources. Even though phosphate can be found in fertilizers, it's more commonly found in soaps and detergents. So phosphate is generally a result of what we put in and around the water that flows into the Middle Fork River. But phosphates also can lead to eutrophication as well. Eutrophication we'll get into in just a few moments. And this leads to fish kills, and it reduces biodiversity, so therefore decreasing the overall health. And here's a picture of a body of water in England, London, the Thames River. And this is excess phosphate that led to eutrophication and formed an algal bloom or an algae bloom. So there are these optimal ranges, these very, very low values that are important for maintaining health. And here's eutrophication. Right, we've got sunlight that enters a body, a river system, or even a lake we could apply this to. And photosynthesis is good, right? It's plants take out carbon dioxide and put in oxygen, and that's good. But here we can have algae, and these algae can form this thin film on the surface of the water, and as they block out sunlight, right, that means these plants are going to be dying. And as they die, decomposition needs oxygen to break down organic matter. So we then further even take out more oxygen. Oxygen is deplenished from the water itself, therefore even further driving the lowering of the overall water health. And this is what's called biological oxygen demand. We're not going to be studying this one for this class. Total dissolved solids is pretty much looking at the solids that are in the water. We're not going to study that one. In coliform. It is important that we know that fecal coliforms are bacteria, that even though they're not pathogenic, they are indicators for the presence of human feces and organisms that live in and around the water. But it has the potential for pathogens. These can be poor septic systems, and we can talk about combined sewer overflows. Sometimes the water goes directly into our riverways, and that's not good. And to be safe swimming, there should be no more than 200 colonies per 100 milliliters. And really, we'll talk about this in an urban setting, and even suburban setting, that coliform levels matter. They matter. This is what allows beaches to be open, even in Lake Michigan. So here we're going to look at dissolved oxygen. Dissolved oxygen has the highest weighing factor. It's the most important feature. And secondly are the fecal coliforms. The coliform amounts, the values between dissolved oxygen and fecal coliform are more important than these other values. Even though these are important, DO, dissolved oxygen, and coliforms are the top two or most important Q values. So here's where we look at what a Q value is. A Q value is a way of standardizing the different water qualities, in this case, that result so they could be combined and used and find overall water quality values for the river. And we can think of these like grades. Less than 50 is a failing grade, whereas 50 or 90 or more is more like an A. So we want our Q values to be high. We want them to be, 80 and above, just like we would want our grade to be. So the overall water quality from 90 to 100% are excellent. Although I've never seen the Middle Fork River be excellent, I have seen it good. It's been good over the last several years. So let's make sure that we do the quantitative study before we evaluate if the water's good or bad. I know a lot of times we come into class and we think of the water in the Middle Fork as being, well, let's just say really crappy, literally and figuratively. And the medium range, still acceptable, is 50 to 69%, and below is bad into very bad. So just like a student earning a grade, the higher the overall water quality, the better the health of the river or stream system. The above table is how we will take numbers and make sense within a comprehensive qualitative explanation of the water's health.